All right, let's talk about some common data science interview questions. So, data science is a very broad sort of job description and it incorporates a lot of things. So, not all interview preps are going to be relevant, but this is generally if you're doing something involving machine learning, you're probably there's a chance that you might be asked technical interview questions like these. Um, so when it comes to probability theory, there's a couple of categories that these questions can fall into, and so um, there's a few key concepts where if you understand these concepts really well, you'll be able to answer a lot of the most common types of interview questions. So this doesn't cover everything, but it covers like a large portion of these things. And so one of the really common interview questions involves Bayes' rule and conditional probability. So when we talk about conditional probability, what we mean is this. Suppose we have two events, A and B. So we have let me finish writing out the formula here. So this is, so if we have two events, A and B, we want to know what the probability is that an event A is going to happen, given that we know that event B has happened. So this is the formula that's used to define it mathematically. And this sort of makes sense because when you're computing a probability using a fraction, typically in the numerator, what you'll put is the some measure of the events which satisfy whatever probability you're looking for. And then in the denominator, you'll put some measure of the possible events that could happen. So, if we're trying to figure out what the probability is that event A happens, given that B has happened, what you're really doing is you're trying to figure out what is the probability that both A and B occur, given that event B has occurred. So in the numerator here, we put the probability of A intersect B because that represents the scenarios in which both event A and event B has happened. But then in the denominator, instead of putting sort of all possible events in the denominator, we're only concerned with events in which scenario B has happened because we're assuming that it has happened. So this is sort of giving us, this fraction is sort of telling us how many ways can we have both events A and B occur, given that we know for sure that event B has occurred. And so that's sort of a way of deriving this formula. And so this is just the definition. So then there is another formula that's useful, and it's called, I guess it makes sense to just write it as Bayes' rule. And basically, oftentimes when we're given this thing, if we want to compute the probability of event A given B, sometimes these events on the right here it's not exactly straightforward how to compute them. It might not be straightforward. How do we compute the probability of A intersect B? And so a formula that ends up usually being very useful is called Bayes' rule. And this says that the probability of A given B, this is just another way of writing this, it's equal to the probability of B given A times the probability of A divided by the probability of B. Another way of, so basically if we want the probability of A given B, the formula, you have to sort of just memorize it, but we take we take this and we flip it. So instead of A given B, we put B given A. And then we have to multiply it by probability of A on top and probability of B on bottom. So it can be sometimes a little confusing to remember. Flipping the A and B is usually sort of easier to remember, I find. And the more difficult thing is remembering what goes in the numerator here and what goes in the denominator. Where does probability of A go and where does probability of B go? And one way to remember it is that if you remember the definition of conditional probability, which in my opinion, it's sort of like a straightforward definition, given the logic that I discussed earlier. Here in this formula, the probability of B is in the denominator. And so that's one way to, and that's the same in this formula as well. And so that's one way to remember it. Another way is that by rearranging Bayes' rule, just multiplying the probability of B on both sides, we get this formula. And of course, like, this is assuming that the probability of B is non-zero, which I guess makes sense, because if you're looking for the probability that A occurs given that B has occurred, if the probability of B occurring is 0, then there isn't really a scenario in which A and B, in which A has occurred and B has also occurred, because B has probability of 0 of occurring. So don't really worry about that. But this is this other formula I have down here is another way of writing Bayes' rule, and it might be a little more easy to remember. There's a little bit of symmetry going on here. And so if that's easier to remember, then you can just memorize this and move this probability of B over to the other side. And in a lot of these, the reason this is useful is that in a lot of these problems that you'll see in interviews, these three things are things that you can actually compute. But actually there's something that's usually a little more useful. And I'll write it down here. I'll write it over here. So the probability of A given B. So of course we have the probability of B given A times the probability of A up here. But usually we don't really know the probability of B directly, but we sort of, what we can do is we can use this, and this uses something called the law of total probability, I believe it's called. It's a little more general than what I'm writing here. So basically what happens is that if you can divide the entire probability space into a number of different events that are disjoint and which together make the entire probability space, then the probability of the event B is equal to the sum of the probability of B given A times the probability of A for every event A in that collection of events which together form the entire event space. So basically you would, instead of this being an addition of 2 terms, it'd be an addition of however many terms you have for each set that you've used to break up the total space. But typically for these sorts of exercises, the thing that you have information for is this scenario where you're breaking up the space of events into 2 pieces. First you have the event A, and then you have A complement, which is just all remaining events. And so what you can do is, to get the probability of B, it's just probability of B given A times probability of A plus the same thing but for A complement. And this sort of makes sense because sort of what we're doing is, if you use this formula up here, you can see that this is just the probability of this is just the probability of B intersect A, and this is the probability of B intersect A complement. And so if you want the probability of the entire set B, then you can consider the probability of B intersected A plus the probability of B intersected A complement. And that the sum adds up to the probability of B because A and A complement combine to make the entire space. So that's sort of some of the logic there. But the idea here is that you just need to have this formula under your belt, memorized however you want. So this is the general formula, and this can get you through a number of exercises. And so let's consider just a random exercise I've sort of come up with. So there's a disease. And 10% of the population is infected. There is a test which accurately identifies infected people pretty well, 95% of the time. So we have 95% accuracy. However, there is a 1% error rate if a person being tested is healthy. So basically, there's a chance that if you're healthy, there's a small chance that you might test positive anyways. Let's say you test positive. How likely are you to be infected? All right. So if you haven't basically, if you've done a lot of these types of questions, you sort of know immediately how to move forward. But if you haven't really seen an exercise like this before, your gut reaction might be, well, the test is 95% accurate. So if we tested positive, the likelihood of being infected is 95% because the test is 95% accurate. But that's not really true. What this 95% number represents is so what we're saying here is the test accurately identifies infected people 95% of the time. So what this is saying is that if you are infected, there is a 95% chance that you will test positive. Or another way of saying that is the probability of testing positive given that you're infected is 95%. So let A be the event that you're infected and let's see here, and B the event that you test positive. This will help us write everything out. So 95% chance that you test positive given that you're infected. So what this tells us is that the probability of testing positive, which is event B, given the fact that you're infected, which is event A, is 95%. All right, so that's what we know. That's one of the things we know from the statement of the problem. And remember, what are we trying to figure out? We're trying to figure out, we've tested positive and we're trying to find the likelihood that we're infected. So what we're trying to figure out here is the probability that we are infected given that we have tested positive. So what we're looking for is the probability of A given B. But what information we have here, among other things, is the probability of B given A. And so that's sort of a giveaway that we want to use Bayes' rule. So to find the probability of A given B, we're going to need the probability of B given A. So let's look at this right-hand side of this equation and figure out everything else we need. So we need the probability of A. So what is A? A is the event that you're infected. So this is basically the event. This is the probability that just a random person in the population is infected. And so here, 10% of the population is infected. And so what that tells us is that the probability of event A is 0.1. And so, of course, that means that the probability of A complement is 0.9 because the two need to add up to 1. Make that see a little nicer. Okay, and what else do we have? We also need the probability of B given A complement. So the probability of B given A complement. So this is the probability that we test positive given that it's not the case that we're infected. And if we remember in the problem statement, there is a 1% error rate if a person being tested is healthy. So the probability that you test positive given that you're actually healthy is 1%. So this is where that 1% comes into play. Let's see here. We got B given A, we got A, we've got, and one thing to remember is that this term and this term are the same, so there's a lot of redoing there. And then we've got probability of B given A complement and this. So that's everything we need. So let's go ahead and write this out. The probability of A given B. We could rewrite the whole formula again here, but I'm not going to do that because it's right there at the top. Instead, I'm just going to start plugging in numbers. So let's see here. We have B given A is 0.95. And then A is going to be 0.01. No, 0.1. So then that goes in the denominator as well. Plus, we have B given A complement, so that's 0.01 times A complement is 0.9. All right, so then we just end up doing a whole bunch of calculations, and it's not very interesting, but it's just a part of the process. 5,009. So this is 0.095 over 0.104. And I haven't actually done a ton of technical interviews yet, so I'm not entirely sure if they would expect you to, if an interviewer would expect you to do this calculation by hand. I imagine they wouldn't. I don't see why they would want to know that and want to see that you do that. But anyways, if you just use a calculator, and whatever this number is, this is the answer. So you have provided an answer, even though this isn't in a form that's easy to interpret yet. But if you use a calculator, this comes out to 0.913 about. So we see that there's actually, it's not drastically lower, but there is a decently lower chance that you're actually positive, that you're actually infected than you may have thought. Instead of a 95% chance, it's down to 91%, or a little over 91%. And so basically what's going on here, if you look at this calculation, is that this, even though there's a pretty small error rate, there is a large part of the population which is not infected. And so that increases this increases the denominator of this fraction, and that lowers the probability that you're actually infected. And so, yeah, that's basically just how you go about doing these sorts of exercises. Basically, what's going to happen is there might be some problem where an interview says, like, well, it's sort of hard to tell, but basically you can sort of start to see the patterns of what indicates a problem like this. Like typically there's some sort of probability that's easy to calculate. And if you really break down the logic, what you're being asked for is sort of like the reverse of the information that you're given. But anyways, as long as you know Bayes' rule, you should be able to do most problems like this without too much difficulty. It's really mostly about memorizing Bayes' rule and being able to recognize when you need to use it. And once you have done that, then these problems become a lot easier. And even if you recognize that it is conditional probability, you really need Bayes' rule. And just again to see that, so using the original formula, that probability of A given B equals the probability of A intersect B over the probability of B. So this A intersect B here, if we were to consider that in this problem, this A intersect B would be the probability that both you're infected and that you test positive. And we don't really have anything in the problem statement that gives us anything related to that. We have information about the probability of being infected if you're a random person in the population, and we know things about what your probability of testing positive is given your status of healthy or infected. But we don't really have any information about combining these two things together. Unless you use the fact that probability of A intersect B is probably probability of A given B times probability of B, and then it just becomes this thing. So you really just need Bayes' formula here. But yeah, that's essentially how you would do any exercise like this.